After D block elements, let us discuss about the F block elements. We know the position of F block elements in the periodic table. They are kept at the bottom of the periodic table. Now, these F block elements actually they belong to group 3 of the periodic table, but they are taken from group 3 and they are placed at the bottom of the periodic table. Now, these F block elements are also called inner transition elements. And we have two inner transition series. The first inner transition series or 4F series and the second inner transition series or 5F series. Now let us see in detail about the F block elements. Now why are they called F block elements? They are called F block elements because the last electron enters the anti-penultimate energy level. It is to the anti-penultimate energy level. Now that is anti-penultimate energy level means n-2 f orbital which are inner to the penultimate energy level. And they form a transition series within the transition series, so they are called inner transition elements. Now what is the general electronic configuration? General electronic configuration of F block elements. n-2 f 1 to 14, n-1 d 0 or 1, ns2. So this is the general electronic configuration of F block elements. Now I told you the F block elements are divided into two series, the 4F series and 5F series. Now 4F series are also called lanthanoids and the 5F series are called actinoids. So in this video we will discuss about the lanthanoids. So next we are going to see about lanthanoids. Lanthanoids or lanthanides or lanthanons. They can be called by any of these names, lanthanoids or lanthanides or lanthanons. Now, what are lanthanoids? They are elements in which the last electron enters in one of the 4F orbital. They are called the 4F block elements or first inner transition series. So, here in lanthanoids, the last electron enters into 4F orbital. They are called the first inner transition series or 4F elements. Now, lanthanum followed by 14 elements. That is, we have the atomic number Z is equal to 58. 58 to atomic number 71. 58 to 71. There is the element lanthanum. Lanthanum atomic number is 57. Now this lanthanum followed by 14 elements 58 to 71. Atomic number 58 to 71 are kept at the bottom of the periodic table and they are the 4F series. So these elements are called lanthanoids and their 4F orbitals are filled. Now the general electronic configuration of lanthanoids is xenon 4F 1 to 14, 5D 0 or 1, 6S2. Because you know this lanthanoids, lanthanum is in the 6th period of the periodic table. So this 4F series, they are from 6th period. And 6th period we have n-2 means 6-2 which is 4F. 4F orbitals are filled first, then 5D orbital, then we have the 6p like that. Now here the general electronic configuration of lanthanoids is xenon 4F 1 to 14, 5D 0 or 1, 6S2. Now I have written here the atomic number, element and the electronic configuration of few elements, few lanthanoids I have written. First I have written about lanthanum with atomic number 57. Lanthanum and its electronic configuration is xenon 5D1, 6S2. Lanthanum 4F orbital is present but it is vacant. Now the filling of 4F orbitals begins with cerium. So cerium is the first element of 4F series, cerium, with atomic number 58. And you can see the configuration: xenon 4F1 5D1 6S2. Now atomic number 63 is europium, EU, with configuration xenon 4F7 5D0 6S2. Next, atomic number 64 is gadolinium with configuration xenon 4F7 5D1 6S2. Now atomic number 70 is ytterbium, YB, with configuration xenon 4F14 5D0 6S2. And the last element of the 4F series is atomic number 71, lutetium, with the configuration xenon 4F14 5D1 6S2. So the first element is cerium of the 4F series, cerium with atomic number 58, and the last element is lutetium with atomic number 71. So atomic number 58 to 71 is our first inner transition series or 4F series. Now you can see the electronic configuration of europium and gadolinium. This is europium and this is gadolinium. Both have 4F7 configuration. Now they take this configuration to get extra stability of half-filled f orbitals. We know f orbital, we have 7 f orbitals, so total 14 electrons can be placed. Half-filled means 7 electrons. So this europium and gadolinium take this configuration to get extra stability. Same way you can see ytterbium and lutetium. It has 4F14 5D0 6S2 and 4F14 5D1 6S2. They take this configuration to get extra stability due to completely filled f orbital. Now let us discuss about the oxidation state of lanthanoids. The common oxidation state exhibited by lanthanoids is +3. All the lanthanoids exhibit +3 oxidation state. Now lanthanoids, they show limited number of oxidation state because the energy gap between 4F and 5D subshell is large. So only limited number of oxidation state is exhibited by lanthanoids. That's the question, why lanthanoids show limited number of oxidation state due to large energy gap between 4F and 5D orbitals. Now other than +3, oxidation state of +2 and +4 is also exhibited by some elements by losing 2 and 4 electrons to acquire stable configuration. Now for example, we can see europium 2+. Europium configuration, you can see what's the configuration of europium. Europium is 4F7 5D0 6S2. So europium is xenon 4F7 5D0 6S2. Now europium takes +2 configuration so that it gets the half-filled 4F stable configuration. Same way, cerium configuration is xenon 4F1 5D1 6S2. Now when I say cerium 4+, 4+ means all the 4 electrons are removed and it gets the configuration of xenon. So cerium can take 4+ oxidation state, and cerium is the only element in the lanthanoid series which shows +4 oxidation state. So that's a question. Name the element in the lanthanoid series which show +4 oxidation state. It is cerium. Same way ytterbium. Ytterbium is YB. YB configuration is xenon 4F14 6S2. Now ytterbium takes +2 oxidation state because you know YB 2+ means it gets xenon 4F14, means stable due to completely filled 4F orbital. Now next we have terbium. Terbium is TB. Terbium. Terbium, electronic configuration of terbium is xenon 4F9 5D0 6S2. Now terbium will take 4+ configuration and it gets the configuration xenon 4F7. But cerium is the element that commonly takes +4 oxidation state. Terbium can also show 4+ oxidation state. Now next we have a question. Cerium 4 plus. Cerium 4 plus is a good oxidizing agent. Why is it a good oxidizing agent? You know, cerium 4 plus means its configuration is xenon 4f0. Now this is a good, already it is stable. 4 plus is stable for cerium, but it's a good oxidizing agent because cerium 4 plus wants to get reverted to stable +3 oxidation state. We know that the common oxidation state of lanthanoids is +3. So cerium 4 plus want to revert to more stable +3 common oxidation state. So it acts as an oxidizing agent and it gets reduced to cerium 3 plus. Now next question is, cerium 4 plus is a good analytical reagent. Analytical reagent means it can be used in analysis, analytical reagent. Cerium 4 plus is a good analytical reagent because the E0 value, answer is E0 for cerium 4 plus, cerium 3 plus is 1.74 volt. It's positive, which means that it can act as an oxidizing agent. So it can oxidize water, but the reaction rate is very slow and hence cerium 4 is used as a good analytical reagent. Now next it's a question to calculate the magnetic moment of cerium 3 plus on the basis of Spinelli formula. So cerium 3 plus means the configuration is xenon 4f1. Now one unpaired electron, so the expression is mu is equal to root of n into n plus 2, so 1 into 1 plus 2, which is equal to root 3, which is equal to 1.73 Bohr magnetron. So this is the answer. Now the next question is, europium 2 plus and ytterbium 2 plus exist, or why europium 2 plus and ytterbium 2 plus act as reductants. Reductants means reducing agents. They act as reducing agents because they want to get oxidized, because they accept one electron and they change into europium 3 plus and ytterbium 3 plus, which is their common oxidation state. Now next we have, after oxidation state, about lanthanoid contraction. And we have already discussed the lanthanoid contraction in D block element. Lanthanoid contraction means a steady decrease in atomic radii on increasing atomic number in the lanthanoids. And the reason for that lanthanoid contraction is due to poor shielding effect of 4f electrons. And the consequences also we have discussed. Now here you have studied the effect of lanthanoid contraction on basic strength of hydroxides. Now we know that when you move across the lanthanoids, the size of the ions decreases. So you can see as you move from lanthanum La3 plus ion to Lu3 plus, the size decreases. So the covalent character of hydroxides increases and hence the basic strength decreases. Thus you can say lanthanum hydroxide is the most basic and lutetium hydroxide, it is thrice, the valency is 3, is the least basic. So the answer is, as you move from La3 plus to Lu3 plus, the size of the ion decreases, covalent character of hydroxides increases and hence basic strength decreases. Now let us see the properties of lanthanoids. Properties. Now the first property is, all lanthanides are silvery white soft metals and they tarnish rapidly in air. Their hardness increases with increasing atomic number. Now samarium, and the symbol of samarium is a lanthanoid, Sm. This is exceptionally hard like steel. Now the second property is they have high melting point. Third property, they are good conductors of heat and electricity. Fourth property is they have metallic luster. Fifth property is about the color of lanthanoids. Now lanthanoid ions are colored both in solid and aqueous state due to, and they are colored only if there is unpaired electrons in the f orbital, and if there are unpaired electrons in the f orbital, then FF transition is possible. FF transition. Due to FF transition, the lanthanoids are colored. Now here we have a question. La3 plus and Lu3 plus is colorless. Why are they colorless? So La3 plus means the configuration is Xc, and Lu3 plus configuration is Xc4f14. Now there is no half filled f orbital, so no FF transition is possible, so they are colorless. Now the next question is about the magnetic property. Lanthanoid ions other than F0, F0 means La3 plus and Cerium 4 plus, they are examples where the f orbital is empty, and F14 type. F14 example, ytterbium 2 plus and lutetium 3 plus. Except these two, these F0 and F14, the other all lanthanoid ions are paramagnetic. Why? Due to the presence of unpaired electron in 4f orbital. So empty f orbital and completely paired f orbital, no paramagnetism is observed. Only if there are unpaired electron in the f orbital, paramagnetic property is observed. Now the lanthanoids readily lose electron and they are good reducing agents. Now the next property is lanthanoids do not have much tendency to form complexes. Why? Because of their large size and low charge density. So these are the physical properties of lanthanoids. Now next let us discuss the chemical properties of lanthanoids. So chemical properties. Now the first members are quite reactive, almost like calcium. So most of the reactions of the first members of lanthanoids are like calcium. But with increasing atomic number, their behavior becomes similar to aluminium. Now here I am going to write few reactions, chemical reactions of lanthanoids, and I am going to write Ln. Ln stands for lanthanoid. Lanthanum is La, that is an element. This is the general representation of lanthanoids, Ln. Okay, now I am going to write the different reactions. The first is reaction of lanthanoids with halogen. With halogen you get LnX3. You get a halide with formula LnX3. LnX3 is a general formula. Now lanthanoids, when they react with carbon at 2773 Kelvin, you get carbide with formula Ln3C, Ln2C3, LnC2. Now next, when they react with oxygen, you get oxide, that is Ln2O3, and this is a basic oxide. Means they produce bases when dissolved in water. Now next is when treated with dilute acids, you get salt plus hydrogen gas is produced. Now the next reaction is when heat with nitrogen. With nitrogen you get lanthanum nitride. Since the valency of lanthanum or lanthanides and nitrogen is 3, you can write the formula as Ln. Now you heat with sulfur, you get Ln2S3, lanthanum sulfide. Now on treatment with water you get hydroxide, LnOH thrice plus hydrogen gas is produced. So these are the different reactions, chemical reactions of lanthanoids. Now next we have the uses of lanthanoids. Uses: lanthanum oxide, that is La2O3. Uses: La2O3. that is used in glass industry for polishing glass and making colored glasses. Now, mixed oxides of lanthanoids are used as catalyst in petroleum cracking. The third use is ceric sulfate. Ceric sulfate is used as oxidizing agent in volumetric analysis. And the fourth use is lanthanoids are used in the production of alloy steels. Example for alloy is a magnesium based alloy called mish metal. So what is mish metal? And write its composition. This is asked for the board exam. Mish metal is a magnesium based alloy, and the composition of mish metal is lanthanoid metals 95%, mish metal contain 95% lanthanoids, then it contains about 40%, lanthanoid metals means 40% lanthanum, 50% cerium and rest other lanthanoids, lanthanoids. Okay, now it also contains iron, 5% of iron, then traces of sulfur, carbon, aluminium and calcium. So this is mish metal composition. Now this use of mish metal is used in bullets, shells and lighter flint. So these are the uses of the lanthanoids. So with this we complete the lanthanoids or the 4F inner transition series. Thank you.